In today's lecture, we will talk about planetary gears. So planetary, or sometimes also called epicyclic, gears. Now I will draw a schematic of the planetary gear, of the simplest one, and we will go through the algorithm that will enable us to calculate the unknown angular velocities of shafts that are not given. However, if you're not familiar with how the planetary gear look like, then you should try to find it on YouTube or on the internet as a 3D model, because otherwise it might be a bit puzzling. So I will draw these schematics. So what the planetary gear consists of is a carrier, let's call it, for example, body number 2. On the carrier, we've got a satellite, or the planet gears, that are in gear with what we usually call a sun gear, and because otherwise that would have 2 degrees of freedom, here is a ring gear. So satellite number 3 and sun gear number 4. So how does it look like from the different angle? So the carrier is something like this, for example. It might have multiple 2, 4, 3, 5, many shafts. Okay, so and here is the satellite. Okay, here is the sun gear, and here is the ring gear. Okay, and these are of course tooth wheels. I didn't draw it, so these are tooth wheels, all of them. Okay, and this is the simplest one. Yeah, they should be the same. Sorry. Okay, and this planetary gear has got 1 degree of freedom, so one of the angular velocities has to be given. So let's say that, for example, this one is given and goes to the right. That would be omega 2, 1, and also dimensions are given. And what we are interested in is to calculate the remaining angular velocities. Therefore, the most important one being the output shaft, that would be omega 4, 1. So omega 4, 1 is unknown, and this is what we want to find out. Okay, so this is a typical mechanism with simultaneous rotations, because there is a lot of motion and all of these objects are rotating. So we have a combined rotations, or simultaneous rotational movement. And here is the algorithm how we can get omega 4, 1 from omega 2, 1. Okay, so the first step is the positive direction of angular velocity. In here, all the axes are parallel. That it doesn't have to be true. For example, for the differential mechanism, in here, we have some axes are in this direction, some are in this direction. Okay, so we will have more directions later on. However, so far we only have the horizontal one. So to the right will be our omega plus. So this is the positive direction of angular velocity. Secondly, we have to find out the positive direction of point velocity. Again, we usually use that above the axis we have plus, below the axis we have minus. Okay, so these two are for velocities, point velocities. This is angular velocity, this is point velocity. Okay. Third step is to find out where we will calculate the symbolic equations for the combined motion. Now, combined motion in here is performed by the planets, okay, by the satellites, body number 3. Because body number 2 is connected to the frame, body number 4 is connected to the frame. So, where will we put together the equations? Well, it should be somewhere advantageous, and that such a place would be in gear, okay? Because the relative motion between 3 and 4 in this case, and between 3 and the frame in this case, are 0. So let's call this point A and this one B, and let's write down the symbolic equation for combined motion of the satellite. So in A, so points and symbolic equations. So in A, 3 with respect to 1, and we can go through the carrier and we can go through the sun wheel. So 3, 1 is 3, 2 plus 2, 1. And at the same time, it's 3, 4 plus 4, 1. And 3 to 4 relative motion between 2's wheel 3, the planet, and the sun gear, number 4, is equal to 0. So in A, and only in A, 3, 4 is equal to 0. So if we put these together, 3, 4 is 0, 3, 1 equals 4, 1, so 4, 1 equals the right side of the first equation, and we will get 4, 1 equals 3, 2 plus 2, 1. Now in B, which is here, we can go through the carrier, and the other side, well, that's the frame, right? Because this ring gear is fixed, okay? It's fixed to the frame. Therefore, through the carrier, 3, 2, 3, 1 is 3, 2 plus 2, 1. And 3, 1 is equal to 0, right? I hope that this is clear, because this satellite, it's got little teeth here, the ring gear has got little teeth here, the ring gear is fixed, therefore this point, point B, is actually a pole of motion of body 3 with respect to the frame. Therefore, the 3, 1 motion is equal to 0, which will give us the second equation. 0 is equal to 3, 2 plus 2, 1. Now we have two symbolic equations that we will solve. So first we will write down the vector equation for each point, which is, well, basically monkey work, right? Because the indexes are given by the symbolic equations, and the point is given by the point where these symbolic equations were made. Therefore, we will have in point A, VA for 1 equals VA 3, 2 plus VA2, 1. And in B we will have 0 equals VB3, 2 plus VB2, 1. Okay, so symbolic equations, that would be step number 5. Vector equations, that would be step number 6. And now we have to write down these scalars, so these are vector equations. And we have to write down the scalar equations, because velocity of the point is always, because we have simultaneous rotations, omega times the distance from the axis of rotation. Okay? So omega A for 1, VA for 1 is omega for 1. Okay, the index is given by the index of velocity, and radius is given by the distance from the point A, to the axis of rotation. And axis of rotation is given by the indexes. So this is axis of rotation with respect to the frame. Therefore, if this is R4, okay, this will be R4, then that's it. Okay. Let's talk about the magnitudes first, and the plus minuses, that's another matter. Okay, we'll get to that later. So VA32, so that's omega 32 times the distance between axis 32, which is here, and the point A, which is here. So that would be R3. Okay, this is R3. Again, let's forget about the signs for time. And here we have VA21. So 2,1 axis is here. Omega 2,1 indexes are the same. Times the distance from the axis to the point. So that would be R4. Okay, not R2, because that would be here. Okay, from the axis to the point, that's the distance. Let's do the same with the second equation. So we will have 0, and we will have omega 32. Omega 32 is here, point B is here, so this distance is R3. Omega 21, okay, VB 21, omega 21, and the distance. So distance, this is the axis, and here is the point. So it's all the way from the axis to the point, which is R4 plus R3 plus R3, right? Yep. Okay, so that would be R4 plus 2R3. Okay, now the signs. Signs are, well, they could be tricky a little bit, because we have two sets of signs. The first one equals to the omega. And we said that direction to the right is positive. So omega 4,1 goes to the right or to the left? We don't know, because this is unknown. Okay? So if we don't know, we expect that omega to be positive. So unknown omegas are expected to be positive. If they are going into the other direction, they will numerically give you a negative number at the end. Okay? Omega 32. Well, it's not given, so we don't know. We expect it to be positive. Omega 21 goes to the right, so it's positive. Omega 32 unknown, we expect it to be positive. 21 is positive. So that's the first set of signs. The second set of signs corresponds to the velocity. Okay, so we will take a look whether the point that we are investigating, A in this example, and B for the second equation, is above or below the axis. Okay, so 4,1 is here. Point A is above the axis, above. positive, plus. 3, 2 is here, point A is below, negative. 2, 1 is here, point A is above, positive. 3, 2 is here, point B is above, positive. 2, 1 is here, point B is here, therefore it's above the axis and it's positive. Okay, so this is plus and plus is plus, plus and minus, minus, plus, plus, and plus. Therefore, we can put together two equations. I will just rewrite it. So we will have omega 41R4 equals minus omega 32R3 plus omega 21R4, and 0 equals omega 32R3 plus omega 21 R4 plus 2R3. And what we get here is that we have two equations. What are the unknowns? Well, omega 41 is unknown, right? We don't know where it is. Omega 32 is unknown. Omega 21 is known, it's given. Omega 32 is unknown, we already have it. Omega 21 is known, it's given. So we have two unknowns and two equations, which we can solve in the matrix form. Okay, I hope that you know how to put this to the matrix form. Just to be sure, so we have two equations and we want to rewrite it into the form of A times X equals B, where these are unknowns. This is the vector of the right sides, and this is the system matrix. Okay, so we will have unknowns, omega 41, omega 32 equals something, and this will be 2 times 2 matrix. So we solve this. Okay, this is simple multiplication, so this is the first equation. This row times this column equals this element. So omega 41 is here. Yes, it is R4. Omega 32, is it here? Yes, R3. It's on the right side of equation, while here it's on the left, so we have to move it and change the sign, so it's R3 here. And right side we have omega 21 R4. Omega 21 R4. Here we have omega 41. Is it here? No, it's not at all, so it's 0. Omega 32, yes, it is here. R3, but it's on the right side, so we have to move it and change the sign, R3. And the right side, well, it's only this term, therefore we will have omega 21 times R4 plus 2R3. So this is the same, this is just a matrix form of this set of equations. If we have more complicated planetary gear, we will have more equations, we will have larger matrices, but the calculation, it's just a set of linear equations, so it's easy. Okay, so that's the example. And just to be sure how to do something more complicated, let's take a look at this little example that I showed you. Okay, so this is the differential. It can be found in every car. So this is the shaft from the engine, and these are the wheels. Okay, if the vehicle is running on a straight road, then it's there is not that much movement here. But if, for example, one of the wheels is blocked, then this is what you will get. Okay. So how do we write down the symbolic? Well, not first the scheme for such a mechanism. Well, we just write it the same way as before. So here we have the one of the wheels. Okay, it's this wheel. Then we have a satellite which is connected to something. Let's forget about it for a moment. And then we have another axle. Okay, so these are the axles. Okay, now the carrier is this little ring around. So in here we have a carrier. Okay, in normal car-like differential we would have another planet here. In this little Lego thing it doesn't matter, so there is a single planet here, and we have a drive gear here. So let's put it directly here, and we have the engine shaft that goes somewhere, and of course we have the bearings here. Okay, so differential does have got 2 degrees of freedom. Okay, so 2 of these angular velocities must be given. So let's call the bevel gear 2, satellite 3, the other bevel gear 4, the carrier 5, and the engine gear 6, for example. Okay, so we have to have 2 given angular velocities. So for example, let's have omega 21 going to the left and omega 61 going up. Okay, so now it's a bit more complicated than the previous example because we have more directions of angular velocities. So first one are 2 with respect to 1, 4 with respect to 1, 5 with respect to 1. These are horizontal. So we will have omega plus to the right, but 3 with respect to 5 is here, 6 with respect to 1 is here. So we will go this direction, for example, and this will be our omega plus. So omega plus, the positive omega, will be to the right and up. For velocities, we have to keep this intact. Therefore, we will have plus and minus above, below the axis. And when we rotate it, then these signs have to rotate as well. So we will have plus and minus above and below the axis, but now it's left and right. So above became left and below became right. So the rest should be straightforward. We will select the point for the symbolic equations. So where are the wheels in gear? Here, A, here, B, and here, C. And we will write down the symbolic equations. So just to be sure that you will not have a problem with this, I'll do that for you. So in here, satellite is number 3, so 3, 1 equals, and we can go through the carrier or through the gear number 2. So it will be 3, 5 plus 5, 1 through the carrier or through the wheel number 2. and in A, and only in A, 3 with respect to 2 is 0, right? Because they would lose their teeth if that wouldn't be true. So 3, 2 is equal to 0. And therefore in A, 3, 1 equals to 2, 1. We put it here and we will have 2, 1 equals 3, 5 plus 5, 1. And we have one equation. In B, again, what body is performing combined motion? It's the body number 3, because it's not connected to the frame through a joint, only through some other bodies. So in B, 3, 1 is, and we can go through the carrier, 3, 5 plus 5, 1, or through the other tooth wheel. So 3, 1 is 3, 4 plus 4, 1. And in B, and only in B, 3, 4 is equal to 0. This motion, relative motion between 3 and 4 is equal to 0. So we put this together, 3, 4 is 0, 3, 1 becomes 4, 1, 4, 1 we can put in here, and we have 4, 1 equals 3, 5 plus 5, 1, and we have the second equation. And the last one in here, well, that's going to be simple, because both 5 and 6 are connected to the frame. So we only have one equation. 6, 1 is 6, 5 plus 5, 1, where 6 with respect to 5 or 5 with respect to 6, it doesn't really matter what body we will put first, is equal to 0. So in C, and only in C, 6, 1 equals 5, 1. And that's our third equation. So we have 3 equations. What's the number of unknowns? Well, we know omega 2, 1, omega 6, 1, but we don't know. 3, 2, 1 is known. 3, 5, we don't know. So omega 3, 5. 5, 1, no idea. 4, 1. 3, 5 already there. Oh, this is 3, 5, sorry. 3, 5, 3, 5, not 3, 2. 3, 5 already there, 5, 1 already there, 6, 1 given, 5, 1 already there. So we have 3 unknowns, 3 equations. So I recommend you finish this example to the matrix form at the end, so you would get necessary practice. And as you can see, it's easy to calculate a differential like this one. That's it.